conducted in our work group. So the aim of the project basically is to improve the approach of doing GWAS on SNP chip data. Old methods have major disadvantages, like in microsatellite and linkage analysis-based methods. You have a low mapping resolution, you have large QTL intervals. When using SNP chips, you have the disadvantage of a low resolution, and when you work with a high genetic variation, like in pigs, it's a big problem. And if you only use isolated F2 designs, you have large LD blocks in these data sets. So to overcome these limitations, our approach is to pool 4 well-characterized F2 crosses into a large joint design, which will lead to smaller LD blocks. And using whole genome sequencing of the founding animals, we will have a very high mapping resolution in the end. The crosses on which this project is based is, one is from Kiel, where 5 Piedrin pigs were crossed with large white and landrace pigs. The 3 Kiel crosses are crosses of Maishan and Piedrin pigs, wild boar and Piedrin pigs, and wild boar and Maishan pigs. Like I said, this data was pooled, and this is the starting point of the project where I came into the game. The 24 founder animals were high coverage whole genome sequenced with about 20-fold coverage of the genome. The F1 pigs, where we have 91 individuals, are low coverage whole genome sequenced with a coverage of 1 to 2-fold. And the pigs from the F2 designs were genotyped with a 60K SNP chip. So the first step was mapping the whole genome reads to the pig genome. For the founder population, I used the most recent genome analysis toolkit version. For the F1, I had to go back to the old version because the new one doesn't support low coverage data. And I combined this pipeline with SAMTools variant calling to get low coverage variants. The next step was haplotype estimation of the F0 generation of the founders to receive a phased data set. And using this phased data set, I imputed the low coverage data to sequence level. So the data set at this point has the same marker density in the founder animals. And in the next step, these data sets were merged. The imputed F1 generation with the founder animals, they were also phased, and then the F2 generation was imputed using the phased merged data set also to whole genome sequencing levels marker density. I decided to use the genome analysis toolkit pipeline because it has, before you do the actual variant calling, it has lots of quality improving steps. And when you filter your variants, this is not done solely with values that come from the sequence machine, so not only based on quality metrics, it's also based on a machine learning approach where the algorithm takes variants that are already known and known to be true to give you a more reliable data set in the end. So I did this filtering, and we came. So what you have to consider when you do filtering with the GATK, that you want to have a transition to transversion ratio of 2.15, which is the dotted line here. So we came out with a filtering threshold of 99.8%, so we kept most of the variants in the data set. These results are based on the leftover of a dbSNP version from the old genome. So we found 20 million known SNPs, about 7.7 million novel SNPs. And concerning indels, we found about 1 million known indels and discovered 5 million new ones. Now the new version has been released, so this number goes down to about 4 million using the new version, and this I think doesn't go much further down, maybe to 4.5 million. For the F1 variant calling, like I said, I used a joint pipeline of haplotype caller and mpileup to improve the calling on this low coverage data. So in the end, we took the intersection of what came out of the haplotype caller, the mpileup, and what's in the founder population. So unfiltered SNPs were about 22 million for the F1 data set. To show you what this step, what kind of impact this step has on the data, so the plots you're going to see are basically these variants that are the intersection between the two variant callers. And this is the interesting part. So these are the SNPs that were filtered out. As you can see, we lose a lot of low quality, but also a lot of high quality variants. If you only look at the Phred-scaled quality score, which is the score of individual bases in the read, we see that we lose mostly low quality variants. So this step of taking the intersection of these two does actually make sense. I did some optimization on the filtering. So I took 6 different unfiltered data sets with lots of different settings, and I checked 288 different data sets, and we came out with these filter settings where 16 million total SNPs were left in the data set with 2 million new ones. The F2 SNP chip data, in the beginning we had 51,000 SNPs in the data set. While lifting them to the new genome, I lost about 7 million. So this is the data I used for the plots I'm going to show next. I already improved that to 50,000, so we're still working on improving the whole analysis pipeline at the moment. So the first trait I'm going to show you is average daily gain. So as far as I'm concerned, what's been found about average daily gain wasn't really clear because of the low marker density on a SNP chip. So we found 2 QTLs, one on chromosome 4 and one on chromosome 7. These are the most significant genes that we found where we had significant variants. The high number of variants for some of the genes the reason for that is because I also included intergenic variants. So the variants were most close to this gene. So genes that make sense for the average daily gain we found are, for example, involved in ketogenesis, cell proliferation, cancer and cell growth, adipogenesis, and were previously associated with average daily gain. The next trait I analyzed was the meat-fat ratio. We found a few QTLs, the most prominent ones on chromosome 1, 2, and 4. So we found lots of significant associated genes. The most important ones are again involved in cancer, diabetes, fat synthesis, insulin metabolism. So this also fits the phenotype. We also found some high impact variants using variant effect prediction. And most of them were missense variants, so changes in the amino acid sequence of the proteins. The third trait I want to talk about is back fat thickness, where we found a very prominent peak on chromosome 7. And the genes we found are associated with skeletal muscle cytoarchitecture, again, cell proliferation, obesity, and cholesterol biosynthesis. And again, for that trait, we have a long list of high-impact variants. So the last trait I'm going to talk about is carcass length of the animals. So we found 2 prominent peaks on chromosome 7 and 1 on chromosome 17. I think this one wasn't described before. And here for the carcass length, we also found genes that make sense in terms of the phenotype. Like one is in humans associated with skeletal dysplasia, which causes small bones. We found one that's associated with height in humans, bone formation, feet conversion ratio, and one that's also associated with the body mass index in humans. So I think this is also a list that makes sense in terms of the phenotype. So concerning the missense variants, we found lots of them in the gene coding for the dystonin protein, especially in carcass length and back fat thickness. So this is, I think, a very promising candidate to influence these traits. But from the point of view of a molecular biologist, you wouldn't maybe want to touch this gene because it has 10 different splice variants with about 100 exons, 23 kb of coding region, and the protein is really huge. And we have to consider that these high-impact variants may be artifacts of the transcript prediction in the NCBI database. So what we're planning to do is to evaluate the imputation accuracy of the whole pipeline. I'm currently repeating the analysis with improved settings. I also want to look at structural variants, analyze the sex chromosomes, and analyze additional traits. We have up to 230 different measurements taken on the pigs, at least for the Hohenheim cross. And functional studies will be carried out on promising candidates with very low p-values and strong evidence for high-impact mutations. These are the people that are involved in the project, and thank you for your attention.